Giacomo is going to talk about a hot topic in the generative machine learning community. It's called diffusion models for images. So we're going to see how these generative algorithms are essentially creating new visual content from scratch based on a piece of text that is given as an input. So Giacomo, tell us more about this fascinating technology that is really taking over content creation.
Yeah. So I will share my screen first. Yeah, so maybe I will start with an introduction, like with words, and then we will deep dive into the technical details. And like the things that I wanted to say is that, as Luca mentioned, generative models using diffusion are really important at the moment because there are multiple companies investing on in these models. They all started with DALL-E essentially, which was by OpenAI, which is a company that first proposed this sort of model. But then in the following, this was, I think, in early March, probably something like this, March or April. But after that, there were other companies that actually quickly catch up with the with the latest innovation by OpenAI, and so we had seen Midjourney and Stable Diffusion, which at the moment I think is the probably most famous one, I guess, because now it has some. I mean, it's free first of all because DALL-E was not free to begin with, so you need to have some credits, and on top of that. Stable Diffusion has been implemented in also Keras and PyTorch and so on. And I think that now it features in the sort of standard library from Keras, so you can actually just, in a way, plug and play it in your notebook or whatever. So it's really being deployed everywhere. Okay, this was just my introduction. I don't know if you have any questions or things that I might ask, or you might ask, or curiosities and anything. Okay, so yeah, I mean, generative models using diffusions are actually pretty cool in their output, but the theory underpinning them is not trivial. I mean, it requires some sort of a good amount of technicalities actually. So I will try to keep it as simple as possible, but if you have any questions, do interrupt me, please. So let me start here with this. So I prepared some slides, and these slides are based on this review here. This one is Understanding Diffusion Models, a Unified Perspective, from this guy from Google. I think there are also some other cool resources. So there are plenty of videos and also other more, well, let's say not research level papers, so something that you could actually read.
Giacomo,
Sure.
For the moment we see your iPad, by the way. Is that?
Yeah, that's correct. Yeah.
Okay, wonderful.
So here we'll try to briefly summarize what the content of this paper is. So the first thing is that I would like to mention that these diffusion models are based on what is known as a Markov chain. This is a sort of fancy name. This is some jargon, I guess, from physics. But I mean, the idea is very simple. We just have a sequence of events here. And the idea of a Markov chain is that there is a sort of map from one event. So let's say the green circle here to, let's say, the blue circle here. And there's a sort of map or function, if you want, that maps the green into the blue. And the cool thing about the Markov chain, or actually the hypothesis of the Markov chain, is that each circle here will just depend on the one that comes before it. So the blue circle will only depend on the green circle, the red circle here will only depend on the blue, and so on and so forth. So in some sense, you have a sequence of steps which are related like one-to-one via some function. And this was pretty abstract, but I want to make it perhaps a bit more clear with some image. So in the case of diffusion models, and this will be the thing that we will be talking about, we will be dealing with images. So here we have this cute picture of a dog here, and what I called before the function, so the thing that was represented by this arrow here on the top, is just like adding some noise. Okay, so you basically take the picture of your dog like here, and then you apply some noise through this arrow, let's say, and what you get is this very noisy image of your dog. And this is the first step, and then you can actually go on over and over. And so if I keep adding noise, at the end I will end up with a complete noise here. Okay, so this is some sort of Gaussian noise, and here we have lost track completely of the origin, right? So we don't have any information here on the dog, which was on the left to begin with. So this is the basic idea. Do you have any questions? I'm not saying this is extremely simple, but I would like to know if you are on par with me.
Yes, for the time being, yes.
So essentially what you're doing is you're destroying the content of the image by adding noise in a principled way.
Exactly. So this thing, of course, we are not generating anything, of course, because we are destroying everything, to be honest. So the question here would be, okay, how do I generate new things? So the crucial idea here is that we would like to reverse this process. So right now we are going in this way, right? So the flow is like this, and it's the same here. So we are adding noise. But the thing that we would like to do is actually go backwards. So starting from noise and regenerate, if you want, the image of your dog or another image of a dog or something like that. And this is essentially what diffusion is all about. So as I was saying, diffusion comes into steps. So the first one is this diffusion process, which means adding, let's say, a small amount of noise. So this small is important from a technical standpoint, but I mean, at this stage, you don't really care that it's small. So let's say that I keep adding noise in different steps like this. And this is the forward process. And this is the actual diffusion. But then we also have the reverse diffusion, which means starting from the noise, I want to go back to the image of the dog that I had in the first place. But there is like a couple of important subtleties here that I wanted to mention. So, well, the first is that, of course, the reverse process is some sort of denoising of your image, quote unquote, right? So you start with complete noise and you want to remove it. But the important thing from a machine learning point of view is that the forward process, which means the addition of noise to the image of your dog, is actually fixed. And by fixed, I mean there are no, so there is no machine learning involved in this case. Okay, so that's completely fixed. So you choose maybe some parameters at the beginning, but these are fixed by the user, let's say. So it's not the machine that is learning any representation or any weight or any whatever. So the point is that the forward process is completely fixed. And the thing that we want to learn and where machine learning actually kicks in is the backward process, so the denoising process. And here is precisely where machine learning is going to happen. So this is the thing that you will train your model upon.
So what's, I have a question. So essentially, so this diffusion model is learned through a denoising process or reconstruction process. What's the difference between this and the typical autoencoder architecture where there is an encoder and a decoder?
Yeah, so this is a good question. And so I think I have a couple of answers to this. So the first one is that the autoencoder, actually, you also learn the forward process, right? Because you don't, so first you learn the forward process because that would be the encoder part of the architecture. So maybe let me just write down what this is for the other guys. So for an autoencoder,
we're still see the same page, by the way.
Yeah, I'm writing. You see that I'm writing, right?
No,
it's
blocked on DM based on Markov chain. Yeah, there we go. Yeah, now we can see important forward process is fixed.
Okay. Well, I'm sorry. I thought that. Well, okay. So you didn't see this image, or did you see this image?
No.
Oh,
now we see.
I'm very sorry.
No problem.
I'm very sorry. Don't know what happened. Sorry. Yeah. So Okay, so maybe you thought I was crazy because I was indicating things that were not on your screen, but okay.
It's all right.
Fair enough. Okay, so yeah. Okay, so now you see that I'm writing. Oh, oops, actually I'm erasing things.
Yes.
Yeah.
Okay, so the autoencoder basically does this. So you start from an image, okay, like this, an image of a person. And let's say that this image has, let's call it dimension n. So it can be described through, I don't know, n pixels or something like this in total, or n parameters. Then you apply to this an encoder, which means that you will, let's say, shrink the content of your image here. So to a smaller number of parameters. So here I'm saying that m is smaller than n. So this is basically the idea. So there is a sort of compression going on, right? So you are reducing the amount of information that you can store. And then there is the reverse process, as Luca was mentioning, that is basically you start from this shrink version of your image and re-expand it through a decoder. And so you will go back to the original image of your person, in theory, at least. So you will go back to dimension n. Okay, so you start from a dimension, you shrink it, and then you re-expand it.
Mm-hmm.
This is the idea of the autoencoder. And the thing that I was mentioning before is that for an autoencoder, both this step and this step, so both the encoder and decoder, are actually things that you can learn through a machine learning procedure. Okay, so your algorithm will learn everything appearing here. And on top of that, it's very important for the autoencoder to work that you actually have this bound here, so that m is less than n. Otherwise, the autoencoder wouldn't just make sense because it would just create an identity, right? So if there is no compression, what the encoder learns to do is simply replicating the input image without any loss, because there's nothing happening. So here there are two things that are different. So first, we don't actually shrink the dimension, so there is no compression going on first.
Okay.
And second, the first part, so let's say what here used to be the E, is actually fixed by us. So there is really nothing to learn.
Okay.
Does this answer your question?
Absolutely. Yeah. Thank you.
Okay. Yeah. So I just wanted to give you a few details here on the forward, and then I'm done. So the forward passing, which means that the thing that it's fixed by us. So one of the questions that you might ask is, how is this fixed? So how do we fix that thing? So first thing is I wanted to mention is that here I was very sort of crude in my description. I guess you're seeing the picture of the dog. If not,
yeah,
tell me, please. Okay. So here I had just two steps. So I had like original image, noisy image, and complete noise. So yeah, two steps essentially, two arrows. But the thing is that when you have a diffusion model, you actually want to, okay, start from your image, arrive at complete noise, but let's say in sort of a, 1000 steps, something like this. So you add noise little by little. So you are not just throwing a whole bunch of noise into your image. Okay. And this is important because when you are then reversing this process, and so you are learning the actual model, let's say, for technical reason, it is important that these steps are actually small so that you add a little noise for each step. So not a bunch of noise, so that you can actually learn little by little how to reconstruct your image. And the other thing that I wanted to say is that when I'm talking about adding noise like some little noise, what I mean is when I say add noise, I just mean that we will add some Gaussian noise to our image. And so this is the first thing. So normal distribution of noise. Second thing is that we will have some parameter here, this beta t. So the index t here just refers to the step number. So we will have first beta at first step, second beta second step, and so on and so forth. And this is essentially the only hyperparameter, quote unquote, that you might want to fix at the beginning. So it's often, so this is a variance actually, and they say that we have a variance schedule, meaning that we will have, of course, a sequence of betas, like here, for instance, and the idea is that we take the first beta to be smaller than the second, and so on and so forth, up to the final beta. So we are adding this little noise. And plus, last thing that I wanted to mention is that the fact that it's a Markov chain, so that there is this dependence of each step to the step before that, is encoded in precisely in this parameter here. So here is basically saying that when we add noise to the image xt, we are actually using the content of xt-1 to add noise, in particular the mean of xt-1. So this is the way the Markov chain is encoded in the process. Yeah, so I think this was already quite heavy. So I just wanted to, well, we already talked about the autoencoder, and I just wanted to mention that with respect to GANs, which are another, so these are generative adversarial networks. And these were, I think, the state of the art for image generation in general, probably up to the beginning of this year, I would say, because now diffusion models are really taking over. So there are some differences, both from a qualitative and quantitative point of view. So quantitatively, GAN is actually better in the sense that it's faster, if you like, because you have a single pass. So it's faster, but in the diffusion models are slower. But if you compare the outcome, so if you compare the image that you have generated through a diffusion model or through a GAN, the diffusion model is actually much better, and it's really, really cool. And plus, there is also the fact that from a technical point of view, the GANs are not so easy to train. So you might find some issues and troubles when you're trying to train a GAN. So it's technically more challenging, I would say. And let me just finish with the fact that when we are using some diffusion models, actually what we can do is that, of course, we are not just trying to replicate the image that we started from, as I was mentioning before, but the idea is that the user is able to input a text, or in general a caption of the image that he wants to see. So the idea is that at inference time, my model will start from the complete noise that we have here. We'll try to reconstruct this image, and the reconstruction is guided by my prompt, so by my caption, if you like. So I could write, essentially create the image of a dog, like white dog with some red thingy on top, or something like this, and this will guide the reconstruction. So in some sense, I am the one choosing up to some point. Of course, there is some arbitrariness in the reconstruction, but the idea is that I have some power in guiding the reconstruction. And that's all I wanted to say for today. If you have questions.
Luca, you're muted.
We have time for 1 or 2 questions, Gramax.
If I can just ask a very quick question. You talk about the difference between GAN and diffusion model, but do we know in the order of speed that we are talking about when we compare them, like slow and fast? What do you mean? You have some? Did you find some values, for example?
Yeah, I'm not. So this is a good question. So I don't know the actual answer. I know that. Well, I mean, of course, depends on your hardware for sure. But the thing is that if you try and play with these diffusion models on the internet, there are some APIs, some things that you can play around with. I think it takes in the order of probably 30 seconds for generating like 3 images, something like this. So it's not super fast. I think that a GAN, I mean, if a GAN is comparable to an autoencoder or something like that, then it's order of a second probably, but I'm not sure. I really don't know. I haven't tested a GAN myself, so
okay,
I don't want to say anything wrong.
More questions.
I don't quite get how the prompt is translated into the image. So I understand how the learning process is done, but then how is text linked to the image that is generated in the end?
Yeah, so that is a good question. Let's see if I have another
I don't know if
reference.
it's written in the paper.
I think this is going to be the subject of another episode, because
yeah, I mean, it's the thing is that it's not easy, of course. So guiding the reconstruction like this it's probably the hard part in general, right? Because otherwise that would be just an autoencoder. But we are exactly trying to,
Match.
guide, I would say, match the description. So, I mean, of course, there is an entire other big topic, which is having a reliable deep learning architecture for understanding what the prompt is. So the thing is that these models are actually combined, some sort of ensemble, quote unquote, in the sense that you of course need some GP3 whatever for dealing with your prompt, and then this will feed into the diffusion model. And this is a big topic, and I don't quite know the answer to that, but I think we can discuss it probably more at length in another episode.
Okay, great. Thanks a lot. Thanks, Giacomo. This is a fascinating topic. We're going to get back to it, I'm pretty sure. And next episode is going to be about, I think, video, diffusion models in video, right? And
if you want, yes.
I don't remember. Or Daniele is presenting Human in the Loop.
Yeah, there is also an episode in Human in the Loop.
Excellent. All right, guys, we're out of time. Thank you very much. Thank you, everybody. And see you next episode.